Hello, everyone. Yashmina, thanks a lot for the introduction and organizing this webcast. Everyone else, thanks a lot for attending this webcast. And if you are here, then I have a bad news for you because it's my first webcast, so I'm not really sure if I learned the speaker console well enough to be able to switch between slides so smoothly, but we'll see. And actually, how many times were you sitting somewhere and somebody told you a bad news about something, for example, about some serious problem with your Hadoop cluster? And how many times did you have an excellent weekend with your family and friends, but suddenly it changed into a work day because the Hadoop cluster was down and no one could use that? And when Hadoop was down, how many times did you spend long hours to fix the problem, and after heroic efforts, you became one of the heroes in your company? And how many times did you try almost everything and you had to give up because you simply was so tired and you needed to go sleep for a while? What are your answers to those questions? My answer to each of those questions is at least once. And it usually happened when we were expanding our cluster, when some configuration settings stopped working, when the master node had troubles coordinating a larger number of slave nodes, when the data was growing very, very fast, and when more and more users were submitting more and more jobs, and obviously when we made serious mistakes. Simply speaking, managing a small Hadoop cluster is a completely different story than managing a large one, and we have experienced it in a hard but very, very exciting way. And it was also sometimes surprising, frustrating, a bit ashaming, but definitely fun, and something that I really wanted to experience. And I experienced that at Spotify. A couple years ago, I was a developer who was implementing Java MapReduce, Pig, and Hive jobs. And I wanted to implement them as efficient as possible. So I learned Hadoop internals, available configuration settings, and I wanted to tweak them. Luckily or not, my administrators were not so happy to change them so often, so I learned how to change them by myself. And de facto, I started operating and troubleshooting a small Hadoop and Edge-based cluster. But one day, I did realize that working on this small Hadoop cluster is something like riding a bicycle. So I decided to join Spotify to drive a real Lamborghini, to really see the real face of big and yellow elephant who stores and processes petabytes of data. And I met this elephant very quickly, and I saw him growing very rapidly. Although I give big love and care to him, he and his friends didn't like me at all. In consequence, we had very interesting problems living together. Some of those problems were caused by me, some of them were caused by the elephant, and now I would like to make them public. So during my presentation, I will talk about 5 real-world Hadoop issues that either broke our cluster or made it very unstable. Each of those stories comes from our JIRA dashboard and is based on real facts. And to make this presentation even more engaging, I will expose real graphs, numbers, even our emails and conversations. For each story, I will also honestly share the mistakes that we made, and I will describe the lessons that we learned. This also includes a mistake that I made. And normally I don't like to talk about it, but today I will make an exception and also will share it with you. I hope that you're ready. So let's start. So half a year ago, immediately after significantly expanding our cluster, one of our data analysts always ran into trouble when he wanted to run more resource-intensive Hive queries. His queries were valid, syntactically correct, and they ran successfully on small data sets, but they tended to fail on larger ones. Surprisingly, other users were able to run exactly the same queries successfully on both smaller and larger data sets. Obviously, it sounds like some permission issues. However, the user had write permissions to HDFS directories and Hive tables. We observed that when this user ran a resource-intensive Hive query, the Hadoop cluster, especially HDFS daemons, experienced some stability problems. For example, the name node became less responsive and even freezed, so that it was losing the connection with the DataNodes and marking them dead, even though the DataNodes daemons were running fine on those servers. In the name node logs, on the other hand, we saw thousands of warnings and exceptions thrown in getUnixGroup method. This method takes a username as an input and returns the list of groups that a given user belongs to as an output by running some Unix command on the name node server. Just to give you some numbers, almost 15,000 warnings and exceptions were thrown and caught only during 8 minutes. And assuming the default settings, Apache Hadoop is a very trusty elephant. The username of a user is simply of a user who is accessing the Hadoop cluster is simply taken from a client machine, and by default it's not verified at all. So one user can relatively easily impersonate another one. On the other hand, what was very interesting for us, the group names of a user who accesses a HDFS cluster are resolved on the name node server using the id shell command. And surprisingly, if a user doesn't have an account on the name node server, then the exit code exception is thrown and caught. And if your job is large, like the Hive query submitted by our data analyst that consisted of thousands of map tasks, then you will see many exit code exceptions because the map and reduce tasks are accessing the HDFS on the behalf of the user. And those exceptions can temporarily overload and freeze the name node, and in consequence, the name node can lose the connections with the data nodes and mark them dead if it takes longer than 10 minutes and a half by default. And it really happened on our cluster because this user who submitted those queries didn't have an account on the name node server, so that the name node was throwing thousands of exit code exceptions. And how could that problem be solved? Obviously, a quick and dirty solution is to create an account on the name node server for each user who accesses HDFS. However, for many reasons, including security, you don't want to give everyone an account on this very important machine. Alternatively, the Active Directory or LDAP could be used for finding information about groups of our users who access HDFS. Fortunately, Hadoop provides a couple of configuration settings for that, and you can find them in in core default XML. We tried them, but unfortunately, they didn't work for us. And they didn't work because we wanted to use a dedicated POSIX groups filter as an additional filter to use when searching for LDAP groups, but this filter is not currently supported by Hadoop. And finally, we find a workaround by using name service switch configuration, where we specify that the LDAP should be the primary source of information about groups of our users. And this means that we solve that problem on the operating system level, not on the Hadoop level. But it worked for us. And there are a couple of important lessons that we learned from this issue. First, the administrator should always know who is going to use the cluster and make sure that each user has the right account, permissions, and access configured. Moreover, the administrator should know who is abusing the cluster, for example, by accessing the HDFS too frequently. And this issue happened to us immediately after significantly expanding our cluster. Obviously, those exit code exceptions were appearing in the namenode logs before the expansion, but our cluster was too small to run enough MapReduce jobs to freeze the namenode for a long time. Obviously, if we had parsed the namenode logs regularly to find errors or exceptions, we would notice this problem before the expansion and completely avoid this issue. Okay, so let's jump to the first part of the second story. We saw many data nodes being marked dead by the name node because they were not able to send a heartbeat message saying, "Hi, I'm still alive," for longer than 10 minutes and a half. Surprisingly, the PS command typed on those machines showed us that the DataNodes daemons were running fine on those servers. And by design, when a data node is marked dead, then a costly block replication process is started by Hadoop. The network usage increases because alive data nodes start recreating missing replicas and map tasks running on the servers that have dead data nodes can only process non-local blocks. And what's more, tasks and jobs can even fail or be not to submitted at all due to block missing exception if we lose access to all replicas of a block that we want to process. And the PS command, as I mentioned, showed us that data node daemons existed on their servers. However, the sudo jstack -s command didn't show us anything interesting. Surprisingly, we noticed that some, but not all, of the dead data nodes were able to automatically rejoin the cluster after some number of minutes. So it looked that they might be blocked by something for some reason. And since we didn't know what was the root cause of that issue, we came up with an idea to temporarily increase the data node liveness interval from 10 minutes to 20 minutes to get some breathing room, hoping that at least a costly block replication process will be avoided for those data nodes which quickly rejoin the cluster. And a following patch was quickly written by me, and this patch sets the heartbeat recheck interval. It sets it to 600 seconds, and this patch was reviewed and deployed by someone else. And according to the formula that is visible on the slide, our new DataNode liveness interval should be equal to 20 minutes and 30 seconds. So it was what we really wanted. And after that, we came up with one more idea. And the idea was just to do other very important stuff after deploying this very simple change. And we didn't measure its impact. And this is actually the moment when the third story starts, because a couple of days later, on Saturday morning, our colleague Anders, who was on call that day, raised an incident ticket saying that a cluster becomes completely unstable around 1 hour after restarting the name node. Sadly, it was true. So each time around 1 hour after restarting the name node, the majority or even all of the data nodes became marked dead, making the cluster completely non-functional. And to attack this problem, we first tried to answer the question, why does it happen each time around 1 hour after restarting the name node? And our first idea was based on our theoretical knowledge of Hadoop. And according to our knowledge, we knew that when the data node initially starts up, as well as every hour thereafter, it sends a block report to the name node containing the information about the block replicas that it currently has. So we thought that maybe the storm of block reports coming from data nodes exactly after the first hours heavily overloads the name node and maybe starts some heavy garbage collection phase that freezes the name node. For us, it sounded like a pretty awful but possible scenario. So to avoid the storm of block reports, we decided to use a configuration setting called DFS, block report initial delay. And with this setting, when a data node starts, it waits a random number of seconds between 0 and the value of that property before sending the first block report. And after the first block report is sent, next block reports should be sent after each hour. So we increased the initial delay to 1 hour so that block reports coming from the data nodes will not be sent at the same time, and it will hopefully reduce the load on the name node. And to avoid any possible garbage collector issues on the name node, we decided to increase the heap of the name node and tweak the sizes of the young and old generations. And unfortunately, changing all those settings requires restarting the name node. And now we knew that the restart would take more than 1 hour, because during the restart, the name node waits for almost all block reports, and now they are sent with a random delay between 0 and 60 minutes. So we knew that it will take more than 1 hour. And what was even worse, it was a sunny Sunday afternoon for us, and the unconditional reaction could be only one in that situation. Let's deploy all those changes to the name node at the same time, so that will solve more problems in fewer iterations. And we did that. And a couple of hours later, we were very happy, because the cluster had been running fine, and it looked that the issue was successfully fixed, and we still had a couple of hours of weekend. So we were very happy. However, a couple days later, unfortunately, we were unhappy because the cluster hadn't been running so well. And it looked that our issue was not successfully fixed because we saw many data nodes being dead again. So we started investigating this issue again, but now everybody works rather independently without any particular reason why. And my first finding was very shocking to me because when I looked deeper into the code, I discovered that the heartbeat recheck interval should be specified in the milliseconds, not in seconds, as I thought. So when I set it previously, and I was thinking that I set it to 600 seconds, I really set it to 600 milliseconds. So this means that the formula for calculating the liveness interval of the data node that was presented on one of the previous slides gave us only 31 seconds instead of 20 minutes and a half. So this explains why the majority of data nodes became marked dead so quickly and often during that weekend. And due to the higher load or heavier garbage collection, the name node was simply freezing for longer than half a minute, causing the data nodes to lose the connectivity. So, yes, and due to this awful misconfiguration, we spent a half of the weekend troubleshooting the cluster, and I felt really guilty. And because it happened during my first month at Spotify, I was a bit afraid of my reputation. So I had a small dilemma whether I should send an email with apologies to my colleagues explaining this mistake that was caused by reading wrong documentation, or I was maybe thinking about trying to silently fix that setting. Finally, I decided to send an email, and actually a couple weeks ago I sent also Polish vodka to my colleagues to make them even more happy. However, at that point of time, the reply that I got was not so bad. And I still, the reply was very, I get the support from my colleagues, and I was still feeling as a member of our team. And to compensate my mistake, I decided to put all my effort to solve that issue. However, my next finding was also shocking and very disappointing to me, because it turned out that we didn't have any storm of block reports coming after 1 hour, because in the version of Hadoop that we used at that time, the block report interval was configured to 6 hours instead of 1. So it means that increasing the initial delay for block reports was not a right fix that weekend. And it means that increasing the heap of the name node and tweaking the garbage collection setting was a right fix. But because we submitted all those changes at once, we didn't know which one was actually solved the problem with the cluster being unstable after 1 hour after restarting the name node. And at that point of time, we didn't fix that problem permanently, because we were still losing a couple of data nodes every now and then, but we learned a lot. And probably there are too many lessons that we learned at this single one issue, but I will try to briefly summarize them. So first, measure the impact of each single change made to the cluster. And if you don't have time or energy to do that, simply don't deploy a change, or maybe find somebody else who can do that. Second, Never make bulk changes to the cluster because you will not know which one was a right fix. And double check a configuration parameter specification because the description can be different in different places and you can confuse milliseconds with seconds. Also, double check your default values because they might be optimized in newer version of Hadoop. Question almost everything, even if it's a simple patch submitted by your colleague 5 minutes after you discussed this change. Share the knowledge, even if you make a mistake. And if you make many mistakes, then maybe give a conference talk or a webcast to others. And what is really important, give a support to your teammates, even if they fail. Thanks to that, they will be double motivated to pay you back somehow. And actually, I was really double motivated to fix that issue with missing DataNodes. And I came back to that issue. And I started learning more about available troubleshooting tools for Java applications, for example, JStack, JMap. And actually, this time, it was a good decision. And as I told before, sudo JStack -f didn't show us anything interesting. However, sudo -u hdfs JStack showed us something really, really interesting. And we saw that almost 500 threads in the dead DataNode process were blocked, were in blocked or waiting state, but only 19 threads were in runnable state. And all those blocks and waiting threads were waiting for the same lock to finish operations related to reading a block, creating a block replica, initializing a replica recovery process, and more. And this lock was held by some other thread that ran into a deadlock. And this deadlock is described in 3 HDFS JIRA tickets. And unfortunately, we didn't have enough hands to implement a patch that fixes that problem. We just wrote a simple watcher script that was periodically checking if the data node is running on the server, but at the same time it's marked dead by the name node. And if it happens, then we simply restart the data node. And it worked fine for us, and in this ugly way we solved that problem. And there are also a couple of important lessons that we learned from that issue. And first lesson is that apart from mastering the Hadoop knowledge, we should also learn as much as possible about all available troubleshooting and monitoring tools and their functionalities, parameters, features. And the second lesson is that we should prioritize the contribution to Apache Hadoop even higher. And we at Spotify, we were probably one of the first companies that ran into that issue, because when we first ran into it, there was only one JIRA ticket created for that. And after a couple of months, 2 more tickets were created, which means that more and more companies ran into that issue. And let's go to next story. And this one is actually the most bloody story that I have ever seen on our Hadoop cluster. In a nutshell, our Hive queries were running extremely long because thousands of their tasks were constantly being killed by someone or something for some unknown reason. For example, this print screen shows that a job was running for more than 12 hours, and it started almost 13,000 of tasks until that moment. However, only 4,000 of map tasks finished successfully, while almost 9,000 of them were killed for some reason. Surprisingly, only 1 task failed, which means that there was probably not any bug in the code. And when looking closer at the killed tasks, each time we saw the same message saying task has been killed unclean by the user. And we started looking for more traces of a crime. And when we looked at the timestamps in the logs from the job tracker, the task trackers, and the map tasks that were killed, we figured out that the job tracker got a request to kill those tasks. We started wondering who can actually send a kill request to the job tracker to kill thousands of tasks. And we quickly identified three main candidates: an angry user, the job tracker that can kill a speculatively running duplicate or all remaining tasks when a whole job is going to fail, and the first scheduler if the preemption is enabled. And if you look at the messages saying that a task is killed uncleaned by the user, you can start thinking that maybe some user is a primary candidate to be the serial killer. However, personally, I know almost all Hadoop users at Spotify, and I can assure you that they are friendly, patient, and respectful to others, so it would be very unfair to assume that somebody was manually killing thousands of tasks from Hive queries. The job tracker had also good alibi because the job itself hadn't failed and the speculative execution was disabled on our Hadoop cluster. So the remaining candidate was the first scheduler, but we didn't have any proof. So we started investigating this issue further, and we noticed that the tasks were usually killed very young, quickly after the start, while the surviving tasks were running fine for long minutes or hours. And we also did realize that for our company-specific reason, our ad hoc Hive queries were running in a dedicated pool. And this was actually the key information because it did remind me from some presentation that I watched in the past that first scheduler tries to kill the newest tasks in oversubscribed pools to forcibly make some room for the starving pools. And at this moment, everything became clear, and a quick look at the first scheduler web interface confirmed that. We discovered that our Hive pool that was running so many tasks and queries was running over its minimum and fair shares for a long time, while the other pools, including the production one, were starving. So in that case, first scheduler was legally killing Hive tasks from time to time to give their slots to tasks from other pools. So first scheduler was simply killing to be kind for others. And having this evidence, we could put first scheduler in prison and use capacity scheduler instead. And actually, today, we are using capacity scheduler, but at that time, we decided to reconfigure the first scheduler to make it more friendly and less aggressive. And how can the first scheduler be reconfigured? And obviously, tuning the preemption timeouts based on the cluster workload could be a way to control the aggressiveness of the preemption of the first scheduler. However, it's easier said than done because those settings require a really deep understanding and knowledge about your workload, which later might change or not. And if you, for example, don't want the preemption, you can disable it. However, Disabling the preemption in our case would just partially solve the problem, only partially, because this issue exposed another problem, which was ad hoc Hive queries overloading the cluster. So finally, we didn't disable the preemption. And having this said, our two problems to solve were to stop killing Hive tasks and stop overloading the Hadoop cluster by a high number of ad hoc Hive queries. And we simply solved that problem by limiting the number of map and reduce tasks that first scheduler can run in the Hive pool. And we also limited the number of jobs that we could run in the Hive pool. And this solved our problem. And the lesson that we learned is very simple, that you should know as much as possible about important components of Hadoop cluster. And first scheduler is such a component, and it shouldn't be considered as a black box that somehow schedules the tasks, kills them, and so on. And the last story today, and during that story, I will talk about the situation when we noticed that some of our nodes were suddenly marked dead by both name node and job tracker. Although we could ping them, we were unable to SSH into them. However, so it often suggests some really heavy load on those machines. And when looking at Gantt diagrams, we have discovered that all nodes that were marked dead had one common issue, a heavy swapping. And if you probably know, in case of Apache Hadoop, the practice shows that heavy swapping of JVM process usually means some kind of unresponsiveness or even death. And what was very surprising for us, only servers that were newly added to our Hadoop cluster were swapping, while the old servers were running perfectly fine. And almost always such an observation means that there is some type of misconfiguration of servers in the cluster. So this is sometimes a good reason why it's good to know when and which nodes were added to your cluster. So our newly added nodes were misconfigured, and at Spotify we use Debian Squeeze that contains following default values of swap-related settings that are available on the slide. And this issue shows that default swap-related settings were not ideal because they caused the swapping of some servers. So let's leave those settings for a moment in order to ask one very important question. Why actually were those nodes swapping? And obviously the answer is because the physical memory on those nodes was too high due to some memory-hungry processes running on those nodes. Normally, it's not so easy to quickly identify those processes. However, at that time, our data analyst or data engineer immediately told us that he submitted a very memory-intensive job to the cluster. And his memory-intensive job created 2,000 map tasks, which was around 10 tasks per node on our Hadoop cluster at that time. And in order to optimize the sort and shuffle phase and avoid spilling to disk in the map phase, this data engineer increased the memory assigned to each task to 1.6 gigabytes. So it means that 16 gigabytes out of 32 of memory available on our Hadoop servers were used only by this job. And obviously there were tasks from other jobs as well, and task tracker, DataNodes, and operating system processes running on that server and consuming own parts of memory. So it was not surprising. A physical memory limit was greatly exceeded. And to prevent from issues like that, heavy swapping on Hadoop nodes must be avoided. And I'm not really sure what is the perfect setting for swap space size. And I talked with a couple of people and I found different opinions. Some people recommend to set swap space size to 0 because Hadoop nodes should never swap. On the other hand, some people recommend to set it to very small value, let's say 500 megabytes, because having a small amount of swap sometimes might allow you to avoid the kernel out-of-memory killer that is started by the operating system under desperately low memory conditions to kill some processes. And when the out-of-memory killer starts, it usually kills the task tracker process and all map and reduce tasks that it starts. So there are two different opinions that I learned, and at Spotify we simply set the swap space size to 0, and we monitor our memory usage aggressively, and we try to never use more memory than our physical memory limits. And additionally, you can set VM.swappiness to a very low value, for example 0 or 5. And VM swappiness is a kernel parameter that controls the kernel's tendency to swap application data from memory to disk. And if it's set to small value, like 5 or 0, the kernel is instructed to avoid swap if it's possible. However, it doesn't guarantee you that the swap will not happen, and we saw that at Spotify. And you can also use a configuration setting that and mark it as a final that tells how much memory developers can use for their map and reduce tasks. And if you set it to 1 or 2 gigabytes, then good developers should probably adapt that. And otherwise, you can consider using the memory-aware scheduler that is available as capacity scheduler and also in Yarn. And what is interesting, I have mentioned that we quickly identified this memory-heavy MapReduce job because one of our data engineers told us about the fact that he submitted such a job at that time. Perhaps you are curious who was this data analyst, and I can only assure you that this data analyst is talking to you now. So this issue learned us that we should always ensure that all nodes are configured in the same way, that we should use good and proven practices related to cluster management, and we should, if our cluster is configured correctly, then a single user should not be able to let the cluster or Hadoop node down by submitting some ugly job to the cluster. You can also, if you need, specify some configuration parameter final and sometimes as a final settings, and sometimes run a stress jobs that verify the health of your cluster. So this was the last story today. I hope that at Spotify we'll have even more in the future. So we are constantly expanding our cluster. We recently migrated to Yarn. Today we are deploying high availability on our Hadoop cluster. So we hope that today we'll not run into any issues, but if we do, then I'm sure that we'll enjoy troubleshooting them. And if you are interested in more stories, I highly recommend to visit my blog called Hakuna Map Data, and I describe some interesting stories here as well. And after a couple of years working with Hadoop, the main lessons that I learned is that Hadoop is like a kid, and it needs love and care, and it will make you proud, but also it will cause problems. Definitely, it will grow and change very quickly. It will bring new friends home, like yarn, cats, and it will surprise you. And very often, it will wake you up at the night. However, this Hadoop is very important for many companies, so it's worth spending the time with it. So now I'm open to questions, and I will be happy to answer if there are some of them. Okay, I see many questions here, and the first one is it's from Arthur. And the question is, what do you use to monitor the cluster? And currently, we are using Ganglia for monitoring and Riemann for alerting. And we are still evaluating some other tools, so in terms of monitoring, so maybe it will change in the future, but currently and for next month, we'll stay with Ganglia. There is a question from JIRA, and the question is, what is the difference between sudo JStack -f and sudo -u HDFS JStack? So the difference is that the later command, sudo -u JStack, without -f, will also show you information about the logs that a given thread has. So thanks to that, we were able to notice that many threads were waiting for the same log that was held by a thread that ran into a deadlock. When we type sudo JStack -f, we don't see any information about the logs kept by our threads. Question from Kirt. What tools is used to deploy the operating system and set things like swap settings in the operating system? So we have a Puppet configuration that sets swap settings on our cluster, and to deploy operating system, I think that we use Duck, but this is a tool that our SRE people are using, so I'm not perfectly sure here. I am reading other questions. So there is a question from A.G. Sanchez, and the question is, do you think that issues you experienced are exclusively due to configuration tweaking, or do you think they are due to how the infrastructure of Hadoop is implemented? So in our case, most of we ran into our issue mostly because of our mistakes and misconfigurations. During the slides, I also talk about one story that where the issue was caused by the deadlock that was available in Hadoop code. So I would say that Hadoop code is very stable. Of course, sometimes there are some bugs there because it's open source project that is growing very fast and many people are contributing to it. But if you configure your Hadoop cluster properly and you follow best practices, I think that you will be able to avoid 99% of the issues. At least 99% of serious issues that may make your Hadoop cluster down or run into some unstable mode. And the last question from Earl. Are there any open large data repositories available that we can use to test our own Hadoop cluster setup? So I'm not sure about what does data repositories mean, but there are available some stress tests for Hadoop cluster. For example, you can run a stress test for the name node, and this test will send many requests to the name node to check if it's able to handle that load. And you can run and find similar tests for your MapReduce layer or for Yarn. So there is something possible to find. And at Spotify, we run the test for the name node to stress it. Okay, I see a couple of more questions that are coming in. So a question from Bill. What version of Java and Hadoop is used by us? So in our case, we were using Java 1.6.0.26, and the stories that I described happened on Hadoop 2, but without Yarn. And now today we are running Yarn. And there are new questions coming in. Can you say what operating system is used by us? From Bill. And the answer is that we use Debian Squeezy. And I don't exactly remember the number, but it was Debian 6.0, maybe 7 or 8. Question from Nathan. What was the biggest challenge? So for me, the biggest challenge was to switch from small Hadoop cluster, because I was operating only 5-node cluster at my previous company. But when I joined Spotify, we had 120-node cluster, and we were growing it all the time. So many configuration settings stopped working, many default values were not accurate, and we had like hard time stabilizing the cluster when we were growing from just tens of nodes to hundreds of nodes. And right now we have almost 700 nodes, and actually before and after each migration we are thinking whether something crashes or not this time again. And the second biggest challenge was capacity planning, because we had 200 nodes and we had to buy 500 new machines, or maybe even more machines. The number of machines that we wanted to buy had to be enough to survive one more year. So we spent a couple of weeks analyzing our HDFS, our MapReduce access pattern, our usage, and based on our observation, we had to made a multi-million-dollar investment to buy a couple of hundred machines for Hadoop cluster. So it was I was very exciting being involved into that process, and it required cooperation with many people from many different teams, and I learned a lot during these tasks. One question from Kirt. What components of Hadoop will you target when implementing high availability? So, to be honest, I don't fully understand this question. Kirt, could you please rephrase that somehow? So maybe I will try to answer the question the best as I can. So what we plan to do is to simply install high availability with manual failover only, and we have one name node already running. We'll take a second master machine where we'll install the second name node. We'll also install 3 journal nodes that will be maintaining the metadata information that will be shared by those 2 name nodes. And like if we talk about the challenges or issues that can happen during that process, so I can say that installing high availability is a very well documented process. You can find in the internet very detailed description step by step how to do that. So it shouldn't be difficult, and you can do that in 1 day, maybe 2, if you would like to puppetize nicely your classes. However, the tricky part in our case is that we have many clients that are accessing the Kafka, that are accessing the HDFS, and they must be compatible with all high availability settings. So we have, for example, Kafka that is writing to HDFS. We have Luigi. We have HTTPFS. We have many custom code written in Java, Python that is accessing the name node by passing its host name. So we had to fix that. We had to generalize that. We also use a snakebite, which is pure Python HDFS client, and we had to implement a high availability support for that. So we did all of that. So this probably like making sure that our client code, our existing code that accesses HDFS works with high availability was probably the most time-consuming task. And so far we tested everything on our testing cluster, and it looks good. So we plan to go today night, and we need to do that during a night to minimize the downtime and not impact so many people working with Hadoop at our company. So I hope that it somehow answers your question, and if not, please just send me an email and I will try to answer it better. And if there are no questions, I will just keep you for 2 more minutes because I have a bonus for you, and my bonus is just a question. And what do you think? What can happen with data engineer after some enormous amount of time spent on simultaneously developing MapReduce job, maintaining a large Hadoop cluster, and listening to perfect music for every moment? And the answer is that this data engineer can start discovering Hadoop and its related concepts in the lyrics of many popular songs. And it actually happened to me because I started hearing that Coldplay, Black Eyed Peas, Michael Jackson, or Justin Timberlake are singing about Hadoop, its ecosystem, internals, and the issues that we have run into. And I put all those songs together and created the first ever Hadoop playlist. So I encourage you to type Hadoop playlist in Google and find it and start listening to it. And of course, feel free to contribute to it by adding more songs that for you somehow relate to Hadoop. Okay, so I see one more question, quick question from Bill. What do you use for configuration management, Chef or Puppet or other? And we use Puppet. So at Spotify, we are a highly Puppetized company, and we use Puppet for everything, for Cassandra, Kafka, Hadoop, and other services. Okay, so